Alright, this is our video for Dalton's Law. It's the last of the gas laws that we're going to cover. And we are going to be on maternity page 109. So Dalton's Law of partial pressure is still following the same standards that we've been using for gas law, and we have three questions. What is Dalton's Law? How do you solve using percent volume? And what happens when you collect a gas over water? And so we're going to look through those questions again on page M109. So Dalton's, there should be an S here. Dalton's law has to do with this ratio of gases. So Dalton's law says in a mixture of gases, the total pressure is equal to the sum of the individual pressures. And so there's three kind of different ways that we can write this. So the total pressure is equal to the sum of the individual gases. But the other part is that within Dalton's law, we know that the total gas pressure is relative to the volume of each of the gases. So the pressure of each gas is relative to its percent of volume. And then lastly, the third type of variation of Dalton's law is that if we collect a gas over water, and it'll always say in the problem over water, that's going to be our key, we have to take into account the vapor pressure of the water pushing up. And so we're going to look through all three of these scenarios and what we might see with Dalton's law. So the first part that I want to talk about is just the total pressure being equal to the sum of the pressures. That word sum means to add up. And so if we think about, a container, and if we know that the total pressure of the container is 760 torr, and they tell us that there are three gases in the container. Gas 1 is 350 torr, gas 2 takes up 175 torr, and they want to know, well, what is the pressure of gas 3? Well, we know that the total pressure is equal to the sum of all of these. So 760 torr, or the total pressure, would be equal to the pressure of gas 1, gas 2, and gas 3. So that would be 350 plus 175 plus our unknown. And so we could just solve for that algebraically, and we could see that if we took 350 plus 175, we would get 525. And so 760 minus 525 gives us 235. So our unknown gas should be 235 torr. And we can always just double check to make sure that's true. So all three of these should add up to our total pressure of 760. So 350 plus 175 plus 235 equals 760. And so that's the first kind of scenario within Dalton's law, is that the total pressure equals the pressure of gas 1 plus gas 2 plus gas 3, and so on. And so we can just manipulate that equation to give us what we want. Okay, so that's the first scenario. The second scenario is that each pressure, or the pressure of each gas, is relative to its percent volume. And so we're going to see that in our next example, but basically that means that if you have, again, a container, and let's say that 75% of the container is gas 1 and 25% of the container is gas 2, and the total pressure is, let's say 7 ATMs, then, and this is the total pressure is 7 ATMs, then according to this ratio, 75% of 7 ATMs is going to equal the pressure of gas 1, and 25% of 7 ATMs will give us the pressure of gas 2. And so if we did the calculation for that, we would see that, let's move my calculator over here. So we would see 75%, remember you have to enter that as 0.75. So 0.75 times 7 would give us 5.25 ATMs of gas 1, and 25% of 7 would give us 1.75 ATMs for gas 2. And so that's when we just use percentages. Remember, percentages always add up to 100, and our total should add up to whatever the original total was, which is going to happen to be 7 ATMs. And so there's a couple of different ways that you can use this. One of the ways that sometimes you end up having to use this equation is, the partial pressure of the gas over the total pressure of the gas is going to be equal to the partial volume of the gas over the total volume of the gases, or the total volume of the container. Same thing here, we say all of the gases are of the container. And so it would be a ratio. But the pressure is relative to the volume. Partial over total is going to equal partial over total when you're looking at pressure and then when you're looking at volume. And so that's a different scenario that you may see, and it may come up in one of your problems that you'll have to come back to. Okay. So, and then we'll talk about over water in just a second, but I want to go through and solve this problem right here. So it says, in a container holding a mixture of gases, the total pressure is 760 torr. What is the pressure due to each gas if it's composed of 2 liters of nitrogen, 3 liters of helium, and 5 liters of oxygen? Okay, so the first thing that I like to do when I'm solving these problems is I like to draw a picture, because the picture really helps me understand what's going on. So I know that the total pressure here is 760 torr. And I know that it's composed of 3 gases. So I'm going to go ahead and divide this into 3. And so I have my first gas, which is 2 liters of nitrogen. My second gas, which is 3 liters of helium. And my third gas, which is 5 liters of oxygen. Remember, oxygen gas and nitrogen gas are those diatomic elements. They're always as 2's. Okay, but that doesn't impact what we're doing here. So 2, 3, 5 gives me a total of 10. So 760 torr, but that's going to be 10 liters of gas. So I need to know what's the partial pressure of each. So what I can do is kind of what I just talked about. The partial pressure over the total pressure is, partial pressure over total pressure is going to equal partial volume over total volume. And so that's what I'm going to do here. I'm going to say, okay, so for each gas, the partial pressure, what I'm looking for, so X over the total pressure of 760 is going to equal the partial volume, 2 liters, over the total volume, 10 liters. And that's going to give me the pressure of N. And then I can do the same thing for helium. So I can say X over 760 is going to equal 3 liters over 10 liters. And that'll give me helium. And then finally, I can do that for oxygen. So I can say X over 760 is equal to 5 liters over 10 liters, and that will give me oxygen. Okay, so again, this is going to be one of those cross multiply and divide situations. So we're going to cross 760 times 2 divided by 10, and I get 152 torr. 152 torr for nitrogen, cross 760 times 3 liters divided by the 10 liters. I get 228 torr for helium, and then 760 times 5 divided by 10 gives me 380 torr for oxygen. If I add those up, 380 plus 228 plus 152, I should end up with 760. That's just a way to check my work. But it's based on this idea of percentages. You could also say that 2 divided by 10 was 20%, and 20% times 760. 20% times 760 is 152. Or you could say 3 out of 10 is 30%, so 30% times 760 is 228. And finally, 5 out of 10 is 50%, and 50% times 760 is 380 torr. So there's a couple of ways that you can solve that, but I prefer the picture and then realizing that if I take the, so let's write this down over here to the side, the partial pressure over the total pressure is equal to the partial volume over the total volume. And you just manipulate the equation. Okay, last one we're going to go over and really kind of explain is collecting a gas over water. And if you collect a gas over water, you have to take into account the vapor pressure. And so that's the new piece that we're adding to this discussion. That's our third way of looking at it, and we're actually going to look at a picture to help us. So sometimes scientists collect a gas over water, and so they'll do the reaction and water will be involved, and so you've got your gas trapped, but there's water at the bottom of the container. Okay, so the total pressure in this container is the pressure of the gas, but we have to remember that water, because we learned about vapor pressure, water vapor also is pushing up, and so it's adding to the total pressure. It's a very small amount, but it is adding to the total pressure. And so the total pressure of this system is going to equal the gas pressure plus whatever the vapor pressure is. Well, we know that vapor pressure is impacted by temperature. So the water vapor pressure is dependent on temperature. Depends on temperature. And so this is actually comes from a table. It's a table of values, and I'm going to be referencing the old textbook, so you'd have to get that from the old textbook area, modern chemistry, but you're going to be able to find it in the new textbook as well. I find it back in the back in Appendix A, where it has all of these tables. You're going to look for the water vapor pressure table. And so you can see that it has the temperature listed and then the pressure in both mmHg and in kPa for each of those. And so if the temperature of the water is 18.5 degrees Celsius, the pressure in mmHg would be 16, according to just the water vapor. Okay, and so we're going to have to use this occasionally to work through some of our problems. But that's the overall goal. So let's just say that the temperature, for example, if the temperature is 25 degrees Celsius, then I would need to go to my table and I would say, okay, at 25 degrees Celsius, the pressure in, let's say we're working in kPa. The pressure in kPa is 3.17 kPa. So I'd have to write down 25 degrees Celsius is 3.17 kPa for the vapor pressure. And let's say that I knew that the total pressure in the problem was 107 kPa. Well, what's the pressure of the gas? Well, we know according to Dalton's law that the total pressure is equal to the parts of the pressure. So if this is 3.17 and this is something, in order to add up to 107, I can say 107, or the total pressure, minus the pressure due to the water vapor. So 107 minus 3.17 is going to give me 103.83 kPa for the gas. And so basically I just had to take into account that the water vapor pressure mattered in the total pressure that we were collecting. Anytime you see this, you'll see collected over water, and you'll always have the reference table available to you. Again, it's in the textbook, and it's textbook table A8. In the old textbook, it's in Appendix A, page 859, and you'd be able to reference that. Okay, so let's just take a second, let's review, and then I'm going to make a second video to go over some more practice problems. So Dalton's law in a mixture of gases, there's three ways that we can look at this, but they're all based on a mixture of gases. So the total pressure is equal to the sum of the parts, and that each gas pressure is relative to its percent of volume, which is what we said with partial pressure over total pressure equals partial volume over total volume. And then lastly, if you see those keywords collected over water, you're going to have to look at a table for the temperature to account for the vapor pressure pushing up. And so that's when you collect a gas over water, you've got to account for the vapor pressure of the water pushing up. So this is Dalton's law of partial pressures on M109.